Hello everyone and welcome to my presentation of the Nobel Prize in Physics from 2006 about the cosmic microwave background radiation and its anisotropy. Here is a quick overview of what I'm going to talk about. First, I want to quickly introduce you to the two laureates which shared the Nobel Prize in 2006, following a short overview of the cosmic microwave background, namely what it is and about its black body nature, to then go on to the measurements made by the satellite COPE, which is about the two main instruments used. And then we get to the actual anisotropy of the CMB, which means that, well, the opposite of isotropy. So we have fluctuations in this measured black body spectra from before. And to end the presentation, I want to give you some information about further research, which has already been done after the discovery which led to the Nobel Prize and is still ongoing. These are the two laureates, John Mather and George Smoot, both US citizens born in 1946 and 1945 respectively. Mather has made his PhD in physics in 1947 at the University of California at Berkeley, and during his work for the Nobel Prize, he was in the Astrophysics Science Division at NASA's Goddard Space Flight Center in Greenbelt. Smoot got his PhD in physics in 1970 from the Massachusetts Institute of Technology, and during the work for the Nobel Prize, he was on one hand a professor of physics at the University of California, but also part of the Lawrence Berkeley National Laboratory, also at the University of California. So first, some basics about the cosmic microwave background. We're talking here basically about the moments right after the Big Bang, where the universe still was like a hot plasma, like a hot primordial fireball, and the photons were still trapped or coupled by electrons and photons. This means basically that the thermal energy of photons was high enough to interact with the electrons and protons, and thus the photons in form of radiation was still bound to the matter. At about 3000 degrees Kelvin, there was basically the first light. At this moment, the thermal energy was still high, but now we have free photons which do no longer interact with the matter and are therefore decoupled, like we have decoupled matter and energy. As I hope all know, the universe is expanding, and due to this expansion, we have a stretching of the wavelengths of this first light. The stretching of the wavelength means the wavelengths get bigger, and thus the frequency gets smaller, and as we all know from physics 3, energy equals to the Planck constant times the frequency. The energy will get lower. We talk here about the thermal energy until today, where we are at approximately 2.7 degrees Kelvin, which are in range of microwaves from 0.1 to 100 millimeters. And also in this range, the black body measurements were made, which I will talk about in the next slide. So basically we have only a visual universe up to the point where it was too hot to be decoupled. or otherwise said, has too high thermal energy. But with these observations of the cosmic microwave background, it is actually possible to see the imprints of the fluctuations of the plasma or the primordial fireball. Um, or differently said, we can see past the point of the visible universe, though only for a small split of time. So the actual first observation was already in 1964 by Arno Penzias and Robert Wilson, which also received the Nobel Prize about the cosmic microwave background discovery in 1978. They actually wanted to measure the radio signals from in between galaxies, but got some disturbance, some annoying noises, which was static and came from all directions. They first suspected it was some dirt, tried to clean the radio telescope, which they used, and also erase all the other possible sources for the noise, such as cities. Big cities nearby were, for example, New York City, and also from our galaxy. And then came to the conclusion basically that it has to be something very old due to the redshift and omnipresence in direction. And well, as we know today, or they already knew back then, it was the oldest signal detected from the very first light, the cosmic microwave background. Due to such a important discovery, obviously there was further research needed. There were several different missions and researchers working on that. There was one that was called U2, which were basically balloons orbiting Earth, still not too high, like still in the atmosphere. But also there was COPE, the Cosmic Background Explorer, which was led by Mather and Smoot, our two laureates from the Nobel Prize of 2006. And this satellite COPE had an approximate orbit of 900 kilometers around the Earth, like it was above the atmosphere, to escape the absorption of radiation due to the atmosphere. It was launched in 1989, and already with the first 9 minutes of measurements towards the northern galactic pole, as you can see in the picture, a almost perfect black body measurement was made. Also for the picture, you can see the data points are so little squares. This is because of the rather conservative 1% error estimates. And also if this 3K radiation really is a relict from back when the early hot universe was in a thermodynamic equilibrium, it should show a perfect black body spectrum, which it did, also according to Planck's law on the bottom, which we had in physics 3. For the axis, you can see here again the frequency in centimeters, so the millimeter part would be about 20 to 200 millimeter, which still should be in the microwave wave band. And on the y-axis, they measured the brightness of the radiation in SI units of watt per Steh-radian square meter Hertz. This was one part of the measurements of COPE. Now, if the universe would have been isotropic as described in the most simple model of the Big Bang, we should have measured it in all the directions of the sky. Like it should have been the exact same black body spectrum, which means there should be no dependency on the angles of the measurement. But this cannot be true, as for galaxies and clusters to be built, it needed some fluctuations, some irregularities from the beginning to not be in a equilibrium. This was the other mission of COPE to be fulfilled, mapping namely mapping the entire sky about these fluctuations. Already Penzias and Wilson noted that there should be an anisotropy, but they actually set the limit of about 10%, which was far too big of a deviation from the actual measured black body spectra. So for the two instruments of the COPE mission, I first want to introduce you to FIRAS, the Far Infrared Absolute Spectrophotometer, which objective was to measure the spectral distribution of the CMB in the microwave length range and compare it to the black body form expected in the Big Bang model. So as you can see on the right side, it's pretty simple for such a important measurement. It's basically just a polarized Michelson interferometer, and then gave the definite cosmic microwave temperature, as already mentioned, of 2.725 plus minus 0.002 Kelvin, as well as the first image of a dipole distribution, which was to be expected from the Doppler shift acting on the black body spectrum, and more on the dipole image in a later slide. And now a bit about the second instrument from COPE, the DMR, the differential microwave radiometers, which were for the search of anisotropies in the cosmic microwave background, so the main part for the Nobel Prize of 2006. They decided to do the measurements on 3 wavelengths, 3, 6 and 10 millimeters. Those were chosen actually because they have the least or galactic emissions in these, so least disturbances, and the two cones gave a angular resolution of about 7 degrees, at which the postulated anisotropes for large-scale structures should be found at a large angle, at some large angle regions. The two cones are 60 degrees apart, and thus measuring temperatures from different directions, as there were no absolute values to calculate with. So two measurements for each wavelength, in total 6 different measurements, 6 different directions and wavelengths in total. In the flowchart on the right, you can see those two cones, namely the antennas, which were modulated with a switch. Then the wavelengths were converted into frequency, amplified, and detected through a diode, and in the end demodulated again due to a switch. All the data points from this instrument, from the DMR, were then plotted over the whole sky and delivered the well-known map of anisotropies, which we will have a look at later. So before we look at the map, we got through COPE just quickly the actual date of the discovery that led to the Nobel Prize was on April 23rd in 1992, and this was, well, basically a historical discovery of the anisotropes through COPE, as already mentioned. And they had a characteristic anisotropy of a relative measurement of the difference in temperature to the temperature of the black body in magnitudes of 10 to the minus 5, or as you will also see in the next slide, the temperature differences were about 30 microkelvin And just as with the cones of the DMR, the structures or the differences were larger, a bit larger than these 7 degrees on the angular scale. There were actually several maps of different experiments such as the already mentioned U2 project and also COPE from Mather and Smoot. And here on the right, we can basically see on top the isotropic black body measurement from Firas from before, with a temperature of 2.7 Kelvin. And in the second illustration, we see a dipole having two peaks on a maximum and on a minimum, with deviations from the black body of about 10 to the minus 3, which means in millikelvin, which wasn't smooth enough to actually see the anisotropes. So the DMR observed the sky for 4 years, where it actually reached a quadruple of measurements in a span on the 10 to the minus 6, so in microkelvin range. And you see this on the lowest image. You can also see this red horizontal stripe, which is the Milky Way, which by the way has a non-black body spectra and is here in this picture not subtracted. So basically those three pictures are an increase of relative sensitivity from 1 to 100 to 100,000 fold. The dipole measurement from before was replicated by different projects. You have also here on the slide another picture, another illustration on the bottom. Well, this dipole measurement actually shows the relative movement of our solar system to the, well, firstly to the Milky Way and then the Milky Way relatively to the cosmic microwave background. And it is estimated from that the solar system moves with about 350 kilometers per second opposite to the expected direction from the rotation of the Milky Way, and well, further that the Milky Way itself and also other giant structures move towards the so-called Great Attractor, which lies in the direction of the zodiac sign Aquarius. The cosmic microwave background already has a redshift from the expansion of the universe, but as we are moving relatively to the CMB, this wavelength is again shifted. It's red and blue shifted or towards and away from us. You can see in the picture on the top right a principle about the blue and the redshift, but it is not to be confused with the colors in the map before, where the red dot at the center stood for a higher thermal energy, so a higher frequency and lower wavelength, which would be a blue shift. By the way, the dipole structure alone was not proof enough that the cosmic microwave background is not isotropic. It could have been only a shift to the relative movement of the observer, or in other words, if the observer was at rest relative to the frame, like the cosmic microwave background, he would actually have seen an isotropic cosmic microwave background instead of the shifted one. You should all be familiar with the ether shift drift experiment of the Michelson-Morley experiment, where an actual light ether was disproved. And here on the other hand is the ether more of a theoretical abstract to better describe the expansion of the universe and to orient in which directions certain structures move. Now briefly about the math behind this. It is basically the relativistic Doppler shift in arbitrary direction, so frequency at the receiver would be equal to the frequency of the source divided by the gamma factor multiplied with the angular factor 1 plus cosine theta. And for us, the source is obviously the CMB, where here also the angular component would or could be dropped if it is only a transverse movement, so which means in 90 degrees. Then according to Wien's law, which we also looked at in physics 3, then the wavelength is inversely proportional to the temperature, and thus as the wavelength is inverse to the frequency must then be proportional to the temperature. So we have a angle-dependent temperature which can be calculated with T0 being the black body temperature of 2.725 degrees Kelvin, and theta is beta is the velocity divided by the speed of light, and here the velocity is the speed of our solar system of about 350 kilometers per second, and this would result in the already presented 0.002 Kelvin plus or minus as a deviation of the black body temperature. So the quadrupole measurement of the COPE satellite gives us already quite a good impression on the young universe of about 375,000 years age. Here on the top of the picture, also subtracted, is the Milky Way now. Basically shows us how the fluctuations of the primordial fireball must have been distributed and where we are supposed to have or find large-scale structures today. More details were delivered with the VMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, had about 33 times more angular resolution and 45 times more sensitivity compared to COPE. It uses 5 frequency bands between 23 to 94 GHz and has an actual goal of angular resolution of about 0.3 degrees with a temperature difference of about 20 microkelvin. The VMAP has and still is further contributing to a broad spectrum of research about cosmology. It contributed already significantly on the inflation theory, the theory that in the earliest time of the universe it expanded 10 to the 21 fold in less than 10 to the minus 21 seconds. So a real, you could say, Big Bang, which is thought to be also the origin of the fluctuations. This is still to be researched on. The VMAP also confirmed that there is equal numbers of hot and cold spots on the map. It also confirmed that the variation in density is slightly larger for big scales than for smaller scale structures. And last but not least, that the universe follows the Euclidean space geometry. Likely no parallel lines will ever cross, and the interior angles of a triangle always add up to the 180 degrees. With this, the presentation ends, and you find my references on the following slide. And thank you for your attention. And if you have any questions, please do not hesitate and post them below the video.